energy, integration of non-dispatchable power in industrial systems, energy efficiency, and associated technologies, having published over 20 articles in international journals and 1 book. He has participated in more than 20 national research projects and contracts with companies, and in more than half of these projects and contracts he has served as principal investigator. Please, Dr. Díaz, read it.
So thank you very much for this introduction. So thank you very much for all of you to stay here today, and also give me the opportunity to say thank you to the invitation to stay here to present our work, in special to Dr. Martinez Melgarejo. So also, it's a pleasure to me to stay here in this marvelous island. I am from one of the neighbor islands. So I hope you really enjoy this talk. So the title is Voltage Profile Analysis and the Performance of a Photovoltaic Substation to Use Different Generation Systems. And also, it allows us to use smaller systems, of course, reducing the operation and maintenance cost. But there is a new challenge, how to manage it, because all the actual grids are not configured to work like that. So let me introduce the Spanish Royal Decree 900/2015. This is the first real net metering law in Spain. This law allows us to make two kinds of installation of the PV power. Type 1, there is not a retribution. All the energy excess will be put inside of the grid for free, but there is not an interconnection fees, and the total power must be less than 100 kilowatts. Type 2, there is a retribution with the market price, but there is an interconnection fees. Also, to back up the system, batteries are allowed, but it's not possible to make an injection from the batteries directly to the grid. It's only a local backup of the system. However, for Canary Island, there is not an interchange fees. This is due because the cost of the generation of the isolated systems is higher than in the mainland. One of the consequences that is possible that we will see in the quick future is we are moving from the radial configuration to the distributed generation, and also it means that there will be an increase of the photovoltaic power plants in the low voltage grids. So we can see here exactly 1 year ago in the neighbor island in Tenerife, the PV production that is in orange, and the wind power generation that is in blue. In the case of the PV, this is not the shape that we expected, that we can see in the books, or that we can see in our simulation. This is the real measurement. And as we can see, in the case of the wind power, we have a strong fluctuation. So this fluctuation are producing that the frequency is not stable on the grid. So we need to manage these kind of things. And also, the introduction of this kind of technology are producing a desirable variation on voltage. In the great part of the time, any kind of backup is needed. A backup, in this case, doesn't mean that you need a battery. It means that perhaps you need another kind of power, combined cycle, gas, oil, and so on, to keep the system working in the correct parameters. What is the problem that we are expecting? Well, actually, in the radial configuration, if we can see the line, the black one, we can see the voltage profile from the substation to the end of the feeder. You can see, of course, due to the resistivity of the cable, the voltage is decreasing. But what happens when we are putting a photovoltaic power plant in the end of the feeder, near of the end of the line? So we can see that there is a voltage profile that is rising, and sometimes is higher than the upper limit of the 7% of the nominal voltage. It's a problem to keep the system working because all the devices are preparing to work exactly between two limits, plus and minus 7%. So in that case, our team, together with the University of Las Palmas de Gran Canaria, Cátedra Endesa, and Endesa Company, decided to have a look what will be done here in Canary Island, because it's expected that here, because there is not any fee to connect the PV power plants, the number of the power plants will increase a lot in the quick future. So we decided to try to answer how we can manage these kind of things. For this reason, we decided to use a PV power plant connected in a low voltage grid in isolated island. So Canary Island, we have 7 islands and several minor islands that are also connected, but only 2 of these islands are connected. It means that we have 6 big grids, isolated one from the other one. Another criterion to select this power plant, the power plant must be more than 10 kilowatts. Why? Because we want to know how that's work, because we are expecting this kind of power plants in the future. And also, to arise the problem, we need that the PV power plant must be far away from the transformation center. So this is the solar map in Canary Island. Sorry, it was not possible to translate the scale. But we can see here that we have more or less between 1,500 and near 2,000 solar equivalent peaks hour per year. So we decided to choose one PV power plant in my island, Tenerife. We are here in Gran Canaria, more or less here. We selected a power plant in a town called Arico with that coordinates. One of the things is that we have trade winds here. It's quite interesting to refresh the PV power plant and keep inside of the operation limit. Also, we have a moderate climate, and also the plant has registered more than 1,800 solar equivalent hours per day. So this is the power plant. This is placed on the roof of a wine cellar. This is the location. The transformer is through this line. There is more or less 940 meters from the transformer to the point of common coupling. The wine cellar has a consumption in 3-phase power with a nominal power about 60 kilowatts, and it's also installed on a capacitor condensator with a power of 50 kilowatts ampere reactive. The PV power plant is split in 2 small ones, one of 25 and the other one with 20 kilowatts with the solar panels and Technics, both inverters. These inverters are a little bit old and they don't allow the regulation in the reactive power. So this is the consumption of the wine cellar. Why we need to have a look at this one? Because we are thinking how manage the net metering. For this reason, we need to know how is the consumption, how is the production, how many energy is injected to the grid. So we can see the profile through the year that from March, more or less, until August, the consumption is not so high because there is not a wine production during this season. You can see in autumn and also in winter, the consumption rise because they are preparing wine. So we decided to use three analyzers, 3 positions for the analyzer. We put one in the point of common couple of the wine cellar, another one exactly in the PV power plant, and also in the transformation center. We were taking measurements every 15 minutes, around 12 days. So this is the profile. We have a problem here. We can see in the line that we call line 2, voltage line 2, the voltage profile is higher than the upper limit. And in the case of the line 1, the voltage is lower several days. And we are not in the peak position during the season. We are exactly here in these days. So we have a problem that when the PV power plant and the consumption is higher, will increase. So we have a look about the power consumption. Oh, what's wrong? There is only 2 lines. Because there was not registered power from the line 2. And what's wrong? The measurement? No. We changed all the measurements, we changed all the device, we measure again, and no, there was not consumption in the line 2. It means that we detected a problem inside of the system. And also the reactive power in the 2 lines, the red one here is the line 2, the blue one is the line 3. Here the line 1 is the green one, and the yellow one is the line 3. We can see that reactive power is also so high due to the compensator. So in the case of the point of common couple of the PV power plant, the production is more or less balanced from the different lines. So it seems that the problem is not going from there. But if we see the production of the line 2 and the voltage of the line 2, it matched perfectly. So in this case, in this line, the PV production is producing over voltage of the line. We had a look at transformation sensor, and there is not any problem. The 3 phases were perfectly working during all the time. They were working in the proper limits. There was not any kind of problem. So we have several hypotheses what is wrong. Due to the voltage imbalance, we thought that perhaps the neutral and the earth are not well connected in the system. And of course, there is an unbalanced power loss through the line. The consequence of this one is the overload of the phases, mechanical stresses in the asynchronous machine inside of the wine cellar, and the decreased load capacity of the line. Possible solution, we can think that it's a compensation of the loads, or also the use 4-wire transformer. The case of the overvoltage, we think that the guilty of the system is the energy injection of the PV power plant. But we also have an excess of capacitive reactive power. So this is translated in the incorrect operation of the equipment and the disconnection of the inverters. We had a look about the data registration of the inverters, and every 4 seconds the inverters were stopped because the inverters were detecting an overload and under voltage all the time. So a possible solution is to use a line voltage regulator, also small inverters, or also a dynamic reactive control in order to decrease the capacitive reactive power of the line. So, thinking about that, together with our colleagues from here, from the University of Las Palmas de Gran Canaria, and also with Endesa, the electrical company, we saw that the combined effect of the excess of capacitive reactive power and the PV energy injection caused the overvoltage of the line. This overvoltage, in combination with the voltage imbalance, caused that the inverters disconnect completely of the system, and it implies an economical loss. Likewise, this continuous disconnection, of course, reduces the incoming. So this is the real case in the blue ones of the production in megawatts of the PV power plant. We can see the ideal case, but was detected a problem in one of the inverters. The electronic of the inverter was damaged by the lining during 2013 and 2014. For this reason, in that case, the production is lower. So the speed of the ideal case that we can calculate with the resource, with the meteorological data, and so on. We can compare with the ideal and the fault. And there is a huge problem inside. And after the lining, the electronic power was replaced in one of the inverters, in the 25 kilowatts inverter. And there was an improvement, not at all, but was an improvement in comparison with the other case. So in terms of the economic point of view, due to the law that is paying this power, they have lost about the 40% of the incumbents. It means more or less 100,000 euros in 6 years that they didn't receive. So this is also an economical problem for the producer. What we can do? Well, the things that we are able to do, model the line and try to fix what are the problems. So after a lot of measurements, we looked at this is more or less the profile of the line. This is the transformer. We have the loads of the customer here. We have the wine cellar here with the shunt filter. We have the PV power plant. And also we have 2 customers after the wine cellar. Here there is a special point because it was meters. From here to here there are more or less 940 meters. The section from here to here is more or less 250 millimeters square. It's expected that this section will be a little bit lower, but after a detected problem, they decide to increase. And here we have money to invest in one of these systems trying to solve this problem. So in the case that we have maximum imbalance, but there is not a PV connected, we disconnect for 1 week the PV power plant. There is not any problem with the voltage in the line. Of course, we can see the same effect that through the line, we are keeping more or less the same level. It means there are not too much customers connected to the line called line 2. And we can see that in the line 1, there are plenty of customers. So we are here 230, and they are more or less placed exactly in the middle. This is the upper limit. This is the lower limit. So when the PV power plant is not working, there is not any problem about that. Well, what happens when the PV production is maximum and the loads of the wine cellar are minimum? So here we can see where is placed the PV power plant, and we can see that also we have the same problem with line 2. If we balance the loads of the wine cellar, they are more or less in the limit, but this one is still so high. In the case that we use the strategy of reactive control, static reactive control, through the capacitor bank that they have, they are still in the limit, but there is not a huge difference between them. In that case, the balancing load and a dynamic compensation reduce a little bit this difference, but they are still more or less in the limit. So, what about a line voltage regulator? Why not? This kind of regulator helps to manage the voltage problem and also increase the grid capacity to connect distributed generation, because it's making a decrease of the voltage profile or an increase of the voltage profile. It's only a transformator with 2 wires, and one of the exit wire is possible to control, to manage, and adjust the voltage level. This is the line, and we carry out 2 kind of simulations. One inside of the line. We cannot see here, this is not exactly in the scale. This is placed more or less in 500 meters, exactly in the house of one of the customers. And this is the other one that is placed exactly in the wine cellar. So with this one, when the voltage is a nominal voltage in the transformation center, here when it's near to reach the upper limit, the voltage decreases and keep inside of the limit. So it should be a very good way to manage this kind of problem. But in the case that the voltage is the maximum, the transformation center, two of the lines present too high before the solution that we are proposing. So depending on the case, it can help or not. What about to put this line voltage regulator in the middle of the line? So we have here in the middle, and they are exactly where must be, but if it's needed to use the maximum voltage in the transformation center, in one of the points is near to reach the limit. So perhaps it should be more interesting not to put exactly in the wine cellar, to put exactly in the middle of the line. So with these strategies, we are passing from around 5% to about 2.7% of variation of the voltage through the lines. Another case is the maximum PV production and maximum load on the wine cellar. So we can see that the voltage is so high. This simulation exactly reflects the actual case that we had measured, because they are reaching more than 250 volts. The maximum was 254. This is so high from the upper limit of for your attention, and of course, thank you very much for inviting me to stay here today. Thank you.
Okay, thank you, Dr. Díaz, for your interesting and clear presentation. So I encourage you to perform a discussion, especially in this new framework in which the new systems are renewable, are forced to be operated with the old system like compensator and loads. So if there are questions.
Good morning. You, in your work, you have tried to. Good morning. You have tried static regulation in your work, as I have understood. Have you thought about dynamic compensation, facts, statcoms, and things like that? Have you tried something by now, or are you thinking about that?
To be honest, when we sent this presentation, we only had this simulation, but we are still making cell simulation, and we just have done, I don't know, 1 or 2 weeks ago, we finished all of them. Yes, facts seems to be perhaps the best control way. Yeah. We have been proving everything to try to give an answer to the owner of the PV power plants, because they are, to be honest, they are losing money. So an investment with this equipment is not so high in order of the incomings that they will receive in the quick future.
But where are you planning to put this kind of solution? At the wine cellar or at the transformer, I mean?
Well, to be honest, we have the possibility to have access to both of them. But the simulation in the 2 points are telling us that perhaps it's not the best way. More or less the middle of the line, is that because I forgot to tell you that there is one of the customers that they are consuming a high power, more or less 10 kilowatts. Exactly there, I think, is the perfect point to put. But this is, of course, only by the simulation. We need to make more calculus to be sure to give exactly the solution to the customer.
Okay, thank you.
Thank you so much.
Paulo Pereirinha from Polytechnic Institute of Coimbra, Portugal. I'm not, thank you for your very interesting presentation. I'm not familiar with line voltage regulators. I suppose there must be three-phase transformers or auto-transformers, something like that.
It's a three-phase transformer, and you can regulate the wire, the quantity of the wire that you can
the
use,
steps. Or
the steps.
Yeah,
in the second part of the transformer.
My question is that you have regulated the voltage, but it seemed equally over the three phases. Would it be possible to regulate it using, for example, single-phase transformers connected as a three-phase bank, to regulate differently each one of the phases so that you could reach a better balance between the phases?
Yes, we are making the simulations about that. The result seems that, of course, in the line 2, if we regulate the line 2, it should be enough. But also there is an underlying question, why the line 2 is presenting a high voltage? In other words, who is the guilty? Okay, perhaps we need to rewire all the line. Perhaps customers are consuming more than it was expected. People who was managing the line at the beginning were using only 1 or 2 lines. Perhaps this is the next step to try to answer from us. But of course, the regulation, we tested in the regulation in the line 2, and it was enough and cheaper, of course. But also, we want to ask what happened when a PV power plant is injecting in a low voltage grid, but not near to the transformation center. This is another problem. We want to know at the end of the feeder. Perhaps with these solutions, we want to have a manual or protocol to elucidate what's wrong in the line. So actually, all the bad things for these guys are good for us because we are testing plenty of different solutions. And also, we are not paying for the implement solution. For this reason, we need to have a look the best solution and the cheapest one for the owner of the PV power plant. Thank you.
Other questions? So, a question about the upper limit of the photovoltaic plant. Since you have fixed a lower limit of about 10 kilowatts. But what's your opinion about the upper limit? Since the problem is emphasized in this case.
Yes, I didn't say, but there is inside of the law there is another sentence, special sentence. You cannot have a PV power plant higher than your contract.
Okay.
So we need to have a look about that, but here in the island that we have plenty of hotels, several industry, we need to observe that limit, what's wrong and what's not. And also Arico is quite interesting because the 80% of the photovoltaic power plants and the wind power plants are connected to the same transformation center in medium voltage, all of them. It's about, there are 2 transformation centers, one together the other one. One is 100 megavolts ampere and the other one is 50 megavolts ampere. But all of them are connected exactly in the same line of 66 kilovolts. Okay. So, thank you.
No more questions? Okay. Thank you again for your presentation.
Thank you.
So let me close the session, and so we can go to the coffee break now. Okay. Thank you for your attention.